Thank you, everyone. It's a pleasure to be here today. My name is Peter. I'm at Continuum Analytics. My Twitter is @Wang, so follow me, tweet at me if you have any objections to any things I present today. Today I'm going to be talking about Python and Spark, but a little more background about myself. I did found Continuum Analytics 3 years ago, but I've been working kind of in this space for about 15 years. Continuum is headquartered in Austin, Texas. My co-founder, Travis Oliphant, is actually the creator of NumPy and one of the co-creators of Scipy. I personally started several of the projects that we work on at Continuum. If you're in the Python community or the Python data community, you're probably familiar with some of them. Bokeh is our interactive web visualization library. Blaze is a computation infrastructure, sort of next-gen NumPy that we've been building. And I also started the PyData conference and really have been shepherding and driving the community around PyData, sort of going from the scientific Python world into the Python for data world. And also I personally sort of started the Anaconda and Conda projects, which hopefully many people here are users of. But my actual background is not in software engineering or even scientific computation, it's in physics, which has given me interesting perspective on kind of the evolution of scientific computing and computing at scale and big data as we see it today. So today I'm going to talk about several different things. I'm going to start with actually a little bit of a retrospective on Python and how Python got to be part of the conversation around big data. I'm going to talk about Scipy and PyData a little bit, and then the kind of the early days of mapreduce and Python for data analysis. And then I'm going to talk about Spark and kind of how Python can play in the Spark world and some of the challenges that people have in that world and how we're trying to address some of them. If we have time, I'll also talk about Blaze. So Python and Scipy actually, I'm not sure how many people here are Python users. Maybe show of hands? Great, that's awesome. So Python itself actually has a very long history in scientific computing. Some of the tools that you guys may be are using today actually are really old, but I prefer to call them mature. But even NumPy is actually relatively recent, right? 2006, not that recent, I guess, but it's relatively recent compared to numeric, which is 95. But the reason why Python has had such a long progression in scientific computing, and it's actually really gained significant mainstream momentum now. If you go to supercomputing, if you go to some of these conferences in each of the different areas of science, you'll find Python coming up all the time. And the reason is because even though it's a high-level programming language and it's very accessible and nice, it actually has incredible performance. And so the high-performance linear algebra libraries underneath the hood, the large data structure and the out-of-core processing, a lot of distributed computing tools have been around for a long time in Python. It plays really nicely with traditional cluster sort of tools. And GPUs and all these other things, you can basically get to a lot of this stuff from Python. And that's one of the reasons why we're talking about Python and not about like Perl or Tcl, which are also somewhat popular historically in scientific computing. But it's really the integration and the fact that Python lets you get this nice kind of high-level interface, but then still access the power underneath the hood. So what happened in terms of the formation and the creation of PyData was that probably about 5 years ago, I think, there were a bunch of these nascent efforts to take NumPy, so numeric Python, and its structured data, kind of not quite a data frame, but its structured data handling facilities. People want to take that to the next level. And there were a number of nascent efforts around providing indices on data, labeling of data. Those coming from the statistics world in R or coming from the database world, this all seems very obvious. But NumPy comes from the numerical and scientific computing world where you just have structured data, very rigidly indexed. And so the idea of providing indices, group by aggregation, statistical transformations, all those things were kind of an add-on to this stuff. And so what ended up happening was that out of all those efforts, Pandas really emerged as the dominant library. A lot of hard work by Wes, Chung, and other folks. And a lot of it was actually the effort that Wes put into documentation and writing the book Python for Data Analysis. All those things have really bolstered the use of Python for the data science and data analytics space. But also additional libraries like scikit-learn, which have been around for a while, got ported into and brought along and used for machine learning and predictive analytics, stats models. Some other graphing libraries grew up around and built on top of matplotlib. And then, of course, that Python notebook as well as a nice way of sharing your analyses and sharing input and outputs and looking at a narrative of analysis. All of these tools emerged out of the ecosystem and have really made this a very strong community, and Python is one of the dominant languages used for data analysis today. And the efforts continue. It's not over yet, right? The story is still being written. At Continuum, we're building several libraries that we think are really exciting, and there's a lot of community efforts around many other areas. It's really bigger than can fit even in one person's head, even from a vantage point that I have organizing the conferences and things like that. So it's just really exciting to see where all that's going. Some of the users of our stuff, these are actually not strictly just big data, although many of them do data processing at scale. They use the scientific stack. A lot of the national labs and a lot of the finance firms use the more traditional scientific stack, but they process enormous volumes of data. But this is not something that is trumpeted very loudly. There's not really that big of an industry conference around Python. When you go to PyCon itself, for instance, a lot of people there don't even know or not even aware of Python's use for data analysis. They just think of it as a competitor to Ruby for web development. So part of my job is educating the other Python users about Python for data. And so with the rise of Hadoop, we saw Python being brought into the Hadoop ecosystem and interoperating with a lot of the different tools and technologies there. There's actually even, the first one I listed there, Disco, it's a native mapreduce library for Python, well, based on Python and Erlang, I guess. But that was not really Hadoop, but it certainly was mapreduce. And several of the other libraries are ones that some of you may have used. StreamParse is integration with Storm, and Impila is a very interesting library from Cloudera to do Python direct compilation to C++ and tied into Impala. So these are all very nice, some of them earlier, some of them more recent. But one of the challenges that I think that was presented to the PyData ecosystem and user community was that it still sort of felt like a bit of an outsider to the Hadoop MapReduce sort of world. Getting access to data and HDFS from Python was non-trivial. If you're a Python user, you could just use things like HDF5, or you could use any sort of columnar stores, right? There's a lot of things you could do in Python land, and some people felt like they didn't need to go to Hadoop. So a lot of these tools really emerged from people who found themselves in Hadoop land and needing to use Python or wanting to use Python. And one of the reasons why I think that the appeal of Hadoop, just kind of native Hadoop itself, to Python users was so limited was because Python users would go and do things like this. So this is actually the author of Disco, went on to form a company called AdRoll, and he wrote this really interesting, I hope everyone can see the slide. He has an interesting compilation and code generation infrastructure that uses our compiler named Numba, and uses multicorn and Postgres, and then hits this like his own custom encoding of data. But he's able to basically do 1 billion rows a second on one 16-core box on Amazon, and he beats out Redshift. And this is actually several years ago, beating out Redshift for a number of different kinds of operations. And so Python users tend to go like off the deep end this way, as opposed to processing row at a time out of Hadoop streaming or something. But what's really exciting about Spark is that Python is treated as a first-class citizen in this world. And so we're really, really excited about that. And Spark is a technology ecosystem. There's so many libraries and components inside Spark that are really interesting and can also tie into other parts of the deeper stack in the Python technology space. So it's a really cool thing to see, and we're very, very excited about all that. In terms of actually using Python within Spark, there's obviously PySpark. I'm actually kind of curious, how many people here use PySpark? Cool. Yeah, and so I'm not going to stand up here and kind of give a tutorial on PySpark, but just for those who haven't seen or haven't used it, it's a really, really nice way to write high-level Python code. If you're familiar with Python, or if you have colleagues that are familiar with Python and don't want to go over the hurdle of learning Scala, you can go and do this sort of thing and get very nice access to most of the APIs that are available on RDDs, and actually Spark Streaming and some of these other things they all have wrappers and they all have interfaces right from Python. And I think this mirrors essentially the development in the R world as well. So Python and R both treated as first-class citizens in the Spark community. Now, one of the things that I will talk about, though, that's, so the interfaces are there. When you're using Python and Spark and PySpark like that, you can call out to any of the other libraries in the Python and PyData ecosystem. But one of the challenges that presents when you have this kind of situation is package management. And it's really kind of it's not as sexy as talking about predictive analytics at scale and all this stuff, but it's actually kind of the pain that hits everyone. You're practicing data science teams in the real world that we see run into these sorts of problems: deployment, package management. Matt, actually, we didn't coordinate on the slides, but his slides talked about it very nicely. How do you manage all these open source libraries? And all this stuff is always coming up in the open source world, new cool things to try. How do you manage that chaos as you're trying to actually run stuff in production? And so deployment, package management, versioning, all these mundane things become actually critical matters. And so the challenge that we've seen when we talk to data science teams, we talk to our fellow Python users about how they're using Spark or even just using Python in its own right, the challenge that they run into are things like package management. And specifically when you're using it in Spark, there is a Java sort of build tool chain and package management system that sort of is not native to how Python manages packages, or how our users are used to using CRAN. And just even getting set up with Python, getting a Python environment set up. We are familiar with, we're aware of a lot of people running Hadoop jobs that go and do a pip install or do a Conda install of some package, and that seems like, for batch that's kind of okay, but when you're trying to do this interactive stuff, when you're trying to take advantage of the full power of Spark, that's a really terrible way to live. So we want to sort of solve some of these problems. And then rapid iteration is another challenge that people have. When you start doing this stuff for real, you're going to have production clusters running stuff that can't go down. The data scientists actually have to go through the ops people to get to those clusters and to tweak things on them. And then likewise, the data scientists want to have their clusters they play with, but they don't want to have to go through the hurdle of going through an IT or ops person every time they want to upgrade one little library somewhere. So just that operational impedance mismatch is something that we see people having trouble with. And so what we've done actually, so I want to talk about today, is a technology, a product called Anaconda Cluster. And you can actually install it freely right now. We do also have enterprise versions available. And it manages both these problems for both data scientists as well as for operations and IT. So for data scientists, it lets you very easily deploy and provision and create clusters on EC2. Right now we have EC2 and DigitalOcean. We're adding OpenStack and other sort of on-prem provisioning facilities. And we manage packages across the cluster. So we manage Python, R, Java, JavaScript, any of these things. Native C++ libraries are handled beautifully. And all this stuff is managed this can be managed by the data science team or by the data scientist. For operations and IT folks, the advantage or what the nice thing that Anaconda Cluster gives you is sort of this robust way of managing runtime state. And people oftentimes confuse that. And I don't know how many people here are either in the ops world or deal with people in the ops world, but there's a lot of technologies there that help you provision and do kind of a one-time setup or get everything to some level of kind of known good run state. But actually managing differential runtime state as you have different jobs going, things like that, that's actually kind of difficult and not really what some of the tooling and the orchestration tools are designed for. So additionally, actually isolating different jobs and isolating different libraries, configurations of libraries, that's also a really tough challenge. It's not really what RPM is designed to do. It's not what Debian packages are designed to help you solve. So those are all the things that we sort of manage. We try to make the data science and ops workflow much smoother with Anaconda Cluster. And at the last little point there is actually very interesting, the idea that this is cross-platform tooling. So it's not only Linux, it's not only using Linux and virtualization technology and you have to run a VM if you're on Windows or Mac. It actually is a cross-platform tool that works on Linux, Mac, and Windows natively. And as you can see in the name, Anaconda Cluster, it is derived from Anaconda, or it integrates with Anaconda, which is our very popular Python distribution for data science and scientific computing. So just to give you a little sense of what that looks like, these two lines, the first line, Conda Cluster Create, and you give it a name, and you give it a profile, in this case, Spark profile, and then I submit my job to run. And that's it. So the configuration files, the two little YAML files that configure the Spark profile and the provider definition, that's all you need, and now you're up and going on EC2 or DigitalOcean. And if you want to destroy the cluster, take it down, then one command. And so that's fairly nice. When I show this to some people, it seems to me like this is how I would like to use it, right? It should be quite simple, fairly tidy to configure. I don't have to muck around with a lot of environment variables, things like that, that really can be very confusing sometimes. Now, before I go to the next little bit and talk about how we manage cluster configuration and cluster state, I want to talk briefly about Conda packages and environments. And I'm not sure how many people here are even familiar with Anaconda or the Conda packages. Show of hands, anyone? Okay, some people, good, great. So just as a brief overview for people who are not familiar, Conda is the package manager inside Anaconda, and there's really two core concepts. One of them is packages, and the other is environments. So packages are just referred to these little bundles of libraries, tools, scripts, even configuration files, and it's language agnostic. So we package up Python packages, we package up the LVM compiler, we package up the entire Python interpreter itself. So on my machine, I have one command I can install Python 3, one command I can install Python 2, or even Python 1, and I can go and play around and not mess up these other Python interpreters. So it's very standalone, and we do have Spark packages now. So Java, Spark, and a lot of tools around Spark, Yarn, so on and so forth. So all those things are Conda packages, and the way that we do this in a way that we can, when we get to environments, we talk about compartmentalized or sandboxed libraries. The way we do this is when we build, we're very, very careful to make sure that all the native libraries, all the linking, all the compiler flags are set correctly so that when we go and install the package, we can go and put it into its own environment and not have it splat something into user local lib somewhere that clobbers something else. So with those as the package, sort of underlying package concept, then we can build these environments, Conda environments. And what they are, they're sort of, you think of them as sandboxes that contain collections of versioned, sort of coherently versioned and tested collections of packages that work with each other, that don't conflict. Some version of libjpeg, some version of zlib from something doesn't conflict with something else. And you can mix and match multiple things. So you have some node libraries, you can have R and Python. You put it all into an environment, and it sits in one little subdirectory, and it's completely sandboxed from all the other packages you might install. And so now when you run a script, if you have an IPython notebook, if you have a Shiny app or some R code that you want to run, all those things can just look at the libraries in that little sandbox. And those of you who are familiar with modern sort of virtualization schemes, like whether it's Vagrant or whether it's Docker or CoreOS and things like this, those are, I consider them very heavyweight, but they really try to solve the same problem from an ops and IT perspective. But we are trying to solve this problem from a data science or computational science perspective. And there, what we really want to do is we want to create an environment, put the libraries into it that I know runs the script or this code, and then let it be. And then when I want to go and work on something new, and I want to use the most up-to-date version of the library, I can go and create a new environment, put those libraries in it, and then not have any interference with the old stuff. So that's really what's really nice about Conda is that, again, it's cross-platform. So we do this in a native way on Linux, Windows, and Mac. On Windows, we respect all these things about roaming profiles and app data, local data, temp, all these various really gorpy system level details. We tweak all that stuff and put it all behind one simple command line tool for people. So with this background, then we look at cluster management with Anaconda cluster. When you have a Spark cluster, you can go and create an environment across the entire cluster. So every single machine creates a sandboxed environment with some name. In this case, I'm actually I'm showing several of the different kind of commands. So you can just list the environments. You can install Python =3. That goes and creates a Python 3 environment that has pandas and Flask. Flask is a web framework for Python. You can go and set env, which basically sets the default environment that all submitted jobs will run under. You can also use environment variables to do that. And you can actually, the last one, pushenv, is very interesting. So a common workflow we see for data scientists is that they play around on their local machine, they have a bunch of notebooks and a bunch of code that works, and then they actually want to go and run on a cluster, right? So in that case, pushenv takes all the libraries and everything they've installed locally in an environment and just mirrors that on the cluster. And again, the key thing here is this is cross-platform. So if your data scientist is on a Windows machine, is on a Mac machine, as long as we have in our repo the Linux builds, when you go and you deploy this on Linux, it will go and install the correct versions of all those libraries on the Linux machine and run the scripts. So you also have some little niceties like being able to remote in and list something across all, if you want to tail the logs across the entire cluster. So these are very simple commands, and they really should be simple, right? Like this is really the way that a data scientist wants to be working out there, wants to be thinking about their data flow. So these kinds of tools, we think will, well, we hope, will help a lot of the adoption hurdles for new technology are not the concepts and technologies themselves, but just integration pain points and deployment pain points and things like package management. So we've really focused on trying to solve those problems based on what we've seen data scientists struggling with out in the field. And so this kind of, we're really, really excited about people doing more things with Python and Spark. We're really excited about a lot of the concepts in Spark. And I see a really kind of long-term future for all these, for this interop. And I think that having tools like this to make it easy for people to play around with Python and get their Python stuff into a Spark cluster, play around with it, we hope that these things will really accelerate the adoption and help kind of both these technologies have a very long and fruitful future together. So this is another example here. One last thing I want to add, actually, I forgot, is that we can actually go and install multiple versions. Because we have Spark as a package, we can install multiple versions of Spark on the same cluster. And you can have some jobs that go and run Spark 1.2, which I think is the most recent one at CDH. And then you can actually go and then install Spark 1.3 and play around with that and not have those installations conflict with each other. So yeah, thank you very much. This has been it's exciting to be here, and I'm hoping that everyone is able to check this out. I'll be around if you have any questions about this stuff. Please come talk to me. I'd love to see more Python usage in Spark. Thank you very much.